everyone. My name is Freddy. I'm currently a master's student here at unicamp in the Laboratory of Applied and Computational Electromagnetics. So here I want to present my work, which was in a partnership with Institute of Training in Telecommunication in Peru. So the code is Bicontrollable, optical and plasmonic waveguide. This is our outline here. I want to start with an introduction, then a motivation, results, and finally the conclusion. So to start the introduction here, I want to give a brief introduction about metasurface. So in the literature, there are many authors that have put external input into metasurface in order to change some properties of that. So there are many inputs here that you can change the external electric field, the magnetic electric field, the magnetic field or the temperature in order to change some transmission, reflectance, or absorbance of some metasurface. So the idea was is to make a control device. So you can input an external electric field, a magnetic field, or a temperature in order to change the transmittance, the reflectance, or the absorbance of this metasurface. But the first question here is, can I make the same result but with another different device? So the answer is we can use waveguides. So if you put external electric field into a waveguide, we already know that you can get a modulator here. Change the properties of the light and then modulate the light. But can we also add, in the same time simultaneously, a magnetic field or a temperature? So you can change in the waveguide the effective index, the group index, the polarization of the mode, or the electric field of the mode. You can change many properties of this waveguide. So you can have, with this input, a controllable waveguide. So this is our motivation here. I want to start this slide or this part saying that integrated photonics is not just silicon photonics. So nowadays, many authors are trying to explore new materials in order to control and in order to design more complex devices, exploiting more optical properties. So the first material I want to introduce you here is one of the I want to use in our design is vanadium dioxide. These are really interesting material because these are two-phase material. You can have an insulator at room temperatures, or you can have a metal at temperature beyond 67 degrees Celsius. So what is happening? Because the refractive index of the material changes in terms of the temperature, even the real part or imaginary part of the material. The second one that I want to introduce is a polymer. In 2021, there is a recent polymer which has a really high electrolytic coefficient called Bay1. So this material has around 1,100 picometers per volt at 1.31 micrometers. So there is another feature here of the material which has a decomposition temperature around 205 degrees. So with these two materials, with these two concepts, with these two approaches here, I propose this Bicontrollable waveguide. But why? Why can you control this waveguide? What kind of control do you have? The first one is the electrical control. When the electrical control is made by the Bay1 polymer. So, as you can know, the polymer can change, I can present electropical nonlinear properties. So you can have external electric field and control the refractive index of this waveguide, or this material, sorry. And the second approach, or the second control that you have, is the thermal control that is made by vanadium dioxide, the first one material that I presented before. So there is here another feature of the materials. In the left hand, you have the real and imaginary part of this material in terms of temperature and a wavelength of 1.55 micrometers. So can you see here, as the temperature increases, the effective index of the material decreases. And in the right side, you have the electrolytic coefficient in terms of the wavelength of the material. So in our case, in our study, at 1.55 micrometers of wavelength, we have 690 picometers per volt. So the other question I want to ask you here is, if this material change from dielectric to metal, can we change from optical to plasmonic in the same wavelength? So that is our result shown. This is our proposed waveguide. There is a result slot waveguide, which have a core of vanadium dioxide, in which have a cladding of a vapor polymer that I mentioned before. So we also put some electrodes here in order to control the electric field that we apply. So as I mentioned, the electrodes and the waveguide are part of the electrical control, and the vanadium dioxide is part of the thermal control. For this waveguide, for this design, we just work with the thin mode. So we also test this waveguide for 3 different gaps, which is a slot part of our waveguide for 180, 200, and 220 nanometers. So the first part is the thermal control. What we found here is that when we increase and the temperature increases, we have a transition from the optical mode to the plasmonic mode. As you can see, this is the C part of the main part of the electric field that is parallel to the Z axis. So we can see in all of these temperatures, most of the electric field is confined into the slot waveguide. So here in more detail, I highlight some points of this graph into this transition. So you can use here is the effective index of the mode, which is propagated through the waveguide, and the group index of the mode. So as you can see here, another interesting feature of the waveguide is that from 76 to 81, there is no mode propagating over the waveguide. So you can have a band here at 1.55 micrometers. Now, for the thermal control. For the thermal control, we have an electrical field applied to the polymer, so we can change the refractivity of the polymer by this equation. So you have here we have even the thermal control and the electrical control at the same time. So when we also change the temperature, we also present a change in the effective field of the waveguide in order of 10 to minus 2. So as you can see, if we use another material like lithium niobate or aluminum nitride, we can have this order in order to 10 to minus 4, 10 to minus 6 approximately. But due to the high electron coefficient of the waveguide, we have 10 to minus 2. And in this case, for the thermal and electrical control, we also have the band here of the modes. So, to finalize my presentation, I want to present here my conclusion. In here, in this work, we design a waveguide which is both even optical and plasmonic modes. So we also present that the thermal and electrical control simultaneously. So we can change the thermal and the electrical control at the same time. And we have a control of the waveguide from 10 to 90 degrees Celsius, and electrical control with a 10 volts applied to the electrodes of the waveguide, and a high change in the effective field of the mode in order to 10 to minus 2. Thank you.
Papers now open for questions.
Thank you for your talk. I would like to know, how does the electro-optic coefficient of your Bay polymer compare with that of lithium niobate?
Lithium niobate have around 300 picometers per watt, if I remember. In this case, it's 1,100.
1,000?
100. At 1.31 micrometers. In our case, for 1.55, it's 690.
Thank you for your talk. Could you give more detail about the estimated attenuation?
We're working with plasmonic, so in the part of plasmonic we have around 15 dB per micrometer in the plasmonic part. It's high due to the plasmonic. 15 dB per micrometer.
Okay,
Detonation, yes.
thank you.
What is the resonance of the vanadium when it becomes plasmonic material? It's in the UV.
I don't understand what the resonance is.
Yes, because if it's a plasmonic material, it should be a resonance associated with it. I think that maybe UV. I'm not sure about that.
In that case, we just consider the dispersion of the material at 1.55 micrometers. So there is some slides used showing how the effectiveness of the material change in terms of the wavelength, in terms of the temperature at one wavelength. So we just apply one wavelength for different temperatures.
All right, well, let's thank the speaker again. Okay, the final talk of the session is going to be given by Felipe Mazzi on organic resist-based fabrication of